So before we start VSPR theory, let's make sure we know how to draw the geometrical structures for this. For linear, the hybridization number is 2. So central atom is surrounded by 2 hybrid orbitals. For trigonal planar, the central atom is surrounded by 3 hybrid orbitals. This is for tetrahedral. And for trigonal bipyramidal, the hybridization is 5, surrounded by 5 hybrid orbitals and the central atom. So for octahedral, hybridization number is 6, and this is how the octahedral structure looks like. The central atom surrounded by 6 hybrid orbitals. And for hybridization number 7, the geometry is pentagonal bipyramidal. And for hybridization number 4, there is a case where d orbital is involved. So this is how the geometry looks like, square planar. Once we are sure about drawing the structures, let's talk about VSPR theory. So in VSPR theory, sometimes the shape and geometry can be same and sometimes those are not same. So let's take a look at both the scenarios. So in first case, in polyatomic molecules which has lone pair. So if you remember, we talked about it in hybridization chapter, like where we say in polyatomic molecules there are two theories, one hybridization and two VSPR theory. So in hybridization, the polyatomic molecules which are used without lone pairs. So in VSPR theory, it can be with or without lone pairs. This is the advantage of VSPR theory. So talking of VSPR theory, so in polyatomic molecules, this is a case where lone pairs are present. So in the case where lone pairs are present, shape and geometry both are different because of the repulsions. Because of the lone pair and lone pair repulsions, the shape and geometry differ. So in the case where no lone pair is present, the shape and geometry both are same. Take a look at this table. But first we are only going to study about no lone pair scenario. That means these things. We're going to ignore these things for a while. And after we studying no lone pair scenario, and then we are going to study the structures with lone pair. So for hybridization number 2, the geometry is linear, hybridization is SP, and shape is also linear because there are no lone pairs, and shape and geometry both are same. So for hybridization number 3, the geometry is trigonal planar, shape is also trigonal planar, hybridization is SP2. This is a case where no lone pairs are present. In a case where lone pair is present, the geometry and shape differs. But we are only going to talk about no lone pairs here. So for 4, tetrahedral and SP3. For 5, trigonal bipyramidal, SP3D. I made a quick summary here for the case without lone pair. So for hybridization number 2, hybridization is SP, shape or geometry is same, which is linear. For 3, trigonal planar. For 4, tetrahedral. 5, trigonal bipyramidal. 6, octahedral. 7, pentagonal bipyramidal. Look at the scenario where lone pairs are present. So for 3, hybridization number, in the case where one lone pair is present, the geometry is trigonal planar as usual. Geometry doesn't differ, but the shape, because of the lone pair repulsions, it differs to V shape. Hybridization number 4, there are two cases. In one case, only one lone pair is present. In the second case, two lone pairs are present. So for first case, the geometry is tetragonal. Of course, the geometry doesn't differ, but the shape is pyramidal. And for the two lone pair scenario, the shape is V shape. I made a quick summary here. It will be easy to remember this, and also it's important to remember this table. So for 3, if one lone pair is present, the shape is V shape. For 4, if one lone pair is present, the shape is pyramidal. For 2 lone pairs, the shape is V shape. For 5, there are three cases for where for 1 lone pair, the shape is seesaw. For 2, bent T, and for 3, linear. So for hybridization number 6, the case where 1 lone pair is present, the shape is square pyramidal. For 2 lone pairs, the shape is square planar. For 7, hybridization number, if 1 lone pair is present, the shape is distorted octahedral. So remember, this table is quite easy to remember also. Now let's understand how we can find out shapes using VSPR theory. So for that, first we need to calculate the hybridization number using this formula. We already studied this in hybridization chapter, right? Like the previous video I made. So half into valence electrons of central atom plus monovalent bonding atom minus charge if any charge is present. So what are monovalent bonding atom? It can be either halogens or hydrogens, basically for which the covalency is 1. And valence electrons for central atom is the outermost electrons of that particular family. For example, for boron family the valence electrons are 3, for carbon family valence electrons are 4, for nitrogen it's 5, for oxygen 6, halogen 7, and inert gases 8. This is simple. So once you find out the hybridization number, we should write whatever we know using that hybridization number. So let's take an example and look at this. For first, let's start with H2O. For H2O, let's calculate hybridization number, which is equals to half into valence electrons of central atom. The central atom is oxygen. Valence electrons for oxygen are 6 plus monovalent bonding atom. Check if there are any monovalent bonding atoms. Yes, there are 2 hydrogens, so write 2, and there is no charge, so minus 0. This is gonna be 4, 8 by 2 4, sp3, and the geometry is tetrahedral. This is all we know about this, right? Like once we find out the hybridization number 4, we know this thing, we know the hybridization and we know the geometry. And now draw the geometrical structure and try to substitute it. So once we know it's a tetrahedral geometry, let's draw this structure, how the tetrahedral looks like. So we already learned about structures in this lesson, right? So we need to draw the tetrahedral, and now try to substitute this thing O, and this is going to be H, and it can be H, and these two are empty orbitals, right? Let's just fill 2 lone pairs here. So now we need to remember this table. For 3, 1 lone pair. For 4, 1 or 2. For 5, 1, 2, 3 lone pairs. 6, 1 or 2. For 7, 1. So for a 3 with 1 lone pair case, what is the shape? It's going to be V shape. And for 4, if 1 lone pair is present, it's pyramidal. And then the next one is V shape if 2 lone pairs are present. This is SBL, seesaw, bent T, linear, and this is square pyramidal and square planar and distorted octahedral. Once we memorize this table, we need to check for which case it belongs to. For example, the hybridization number is 4, right? Now check in this case whether we have 1 lone pair or 2 lone pair. We have 2 lone pairs, 2 empty orbitals, so just we put in 2 lone pairs. Now check which shape it's gonna be. It's gonna be V shape, right? More examples to make this concept clear. So here we can let's try with this example, hydronium ion, that is H3O plus, right? Now let's write down the hybridization number. Step 1, half into valence electrons of central atom. What is the central atom? Oxygen, 6, plus number of monovalent bonding atoms. There are 3 monovalent bonding atoms plus 3, minus if there is any charge present. There is a 1 plus charge, so plus 1. Now 9 minus 1 is 8. 8 by 2 is going to be 4 again. So 4 for 4, sp3 and tetrahedral geometry. We know this. Now we need to draw this geometry. So now substitute hydronium ion in this geometry. So oxygen, hydrogens, and here it's an empty orbital, so we put in 1 lone pair. So now using that table, we know for 4 it can be either 1 lone pair or 2 lone pair, and for 1 lone pair the shape is going to be pyramidal, and for 2 it's going to be V shape. So this is a case which involves pyramidal shape. So this is how we're going to find out shapes. Let's take few more examples. I3 minus. So for I3 minus, we should elaborate this first. So I2 and I minus. And now let's find out the hybridization number. Half into valence electron of central atom. Central atom is this iodine. So 7. Iodine belongs to halogens family. So for halogen family, valence electrons are 7. 7 plus check if there are any monovalent bonding atoms. The monovalent bonding atoms means we shouldn't consider the central atom even though if it is monovalent bonding. we only should consider hybrid orbitals. So that means two iodines are present which are monovalent. That means the covalency is 1. So we need to write down 2 and minus of minus charge is present here. So 9 plus 1, 10, 10 by 2, it's going to be 5, sp3d, 1, 2, 3, 4, 5. So the geometry is going to be trigonal bipyramidal. Since we know the geometry, we need to draw this geometry. Trigonal bipyramidal. So central atom surrounded by 5 hybrid orbitals, and now we know we need to just substitute this into here. So I, and 3 lone pairs, 3 empty orbitals, we just put in 3 lone pairs here. Now let's take a scenario, let's write this scenario. We have hybridization number as 5. For 5 we have 1 lone pair, we have a case where there are 2 lone pairs and also 3 lone pairs. For this, for 1 lone pair, the shape is going to be seesaw. For 2, it's going to be bent T, and for 3, it's going to be linear, right? So now check which case it belongs to. We have put in 3 lone pairs here, so it belongs to this shape, and the shape is going to be linear. So for I3 minus, the shape is linear. So this is how we find out shapes using VSPR theory.